Chemistry is not perfect. Well, I think it is, but a lot of people disagree. In particular, reactions are not perfect. When we have a chemical reaction and we write it up as a chemical equation, what we are often doing is making an assumption. We are assuming that all the reactants end up as products. And this is not always the case. What we're kind of saying here is that the reaction goes to completion. But that is not always the case. There could be a bunch of different reasons for why this isn't the case. Maybe not all the reactants react. Maybe the reactants react and form other things. Or maybe the reaction itself is reversible, so the products actually reform the reactants. Either way, there could be a number of reasons for why not everything ends up on the product side. A way to measure this and quantify this is to use the measurement called percentage yield. So percentage yield is given by the formula actual yield over theoretical yield times 100. Actual yield is how much you actually produce in a reaction, normally measured by things like mass. Theoretical yield is how much you expect to produce, normally measured or calculated using things like molar ratios. You then divide actual by theoretical and times by 100. So let's look at this in context of an example. If we were to take copper carbonate, which is normally a green powder, and it's in solid form, so we're going to write the symbol solid, and we heated it up in a crucible. So let's draw ourselves a little crucible here and put ourselves a little bit of green powder. What happens at the end of this heating process is the copper carbonate actually turns into copper oxide and carbon dioxide. The copper oxide is also a solid, but it's a slightly darker, fine black powder. The carbon dioxide is a gas, and that escapes. So what we do is, if we run this reaction through and we weigh it at the end, we can get some idea of how much copper oxide is produced and how much carbon dioxide has escaped. We can use these measurements to try and work out yield. Okay, so let's say we go ahead and we heat our copper carbonate, and then gradually over time, most if not all of that green powder turns into this blackish powder that we associate with copper oxide. Let's say we've weighed the mass of the powder at the start and the end. At the start we had 5.00 grams, and then at the end we had 2.40 grams. Now we have to make some assumptions here. Firstly, we're assuming that the mass at the start is entirely copper carbonate, and then the mass at the end, we can do a few things with that number. Let's say for this case, we're going to assume that all of that 2.4 grams left behind at the end is the copper oxide. We make that assumption so we can do this next calculation. So for the moment, we're going to say 2.40 is the actual yield. Now there are a lot of assumptions and issues with this, with saying this, but just for the sake of this calculation, we're going to say that. There are a few other ways to get actual yield. We can also focus on the carbon dioxide separately, collect it and weigh it and measure it and things like that. But for the moment, we're going to focus in this way. So now how do we find theoretical yield? Well, to do so, we have to start with our copper carbonate. We know we have 5.00 grams of this stuff. We need to first turn this into moles so we can use a molar ratio from our equation. To do so, we need our molar mass formula. So number of moles equals mass over molar mass. Now the molar mass of the copper carbonate, depending on which periodic table you use, you might get slightly different values, but in this case, when we work it out, we get 123.55, and we get that, of course, by adding the molar masses of copper, carbon, and 3 oxygens together. So let's finish this calculation off. We have 5.00 divided by 123.55. And this gives us roughly 0.04225 moles of copper carbonate. Try and leave it in as many decimal places as you can for the moment. Don't round off yet. You can also store this number on your calculator so you have the full digit. Okay, so the moles of copper carbonate are 0.04225. The next thing we need to do is to use a molar ratio from our equation to go to the moles of copper oxide. Now the molar ratio of copper carbonate to copper oxide is 1 to 1, right? But get into the habit of writing molar ratios anyway, and do the do the ratio bit. Okay, so the moles of copper oxide should be 0.04225 divide by the ratio number of the thing we're starting with, which is 1 in this case, coming from here, times by the ratio number of the thing we're going to, which is copper oxide, which is 1. Now, happy coincidence, in this case, dividing by 1 by times and timesing by 1 gives you the same number, but doesn't matter, we've gone through the process anyway. 0.04225 moles of copper oxide are expected to be produced. So the next thing we need to do is convert the moles of copper oxide we've just worked out back to mass. To do that, we need our moles over molar mass formula again. Now the way we use that is we go mass equals number of moles times molar mass. Now the number of moles we have here is 0.04225. The molar mass of copper oxide, which we get by adding the mass of copper and oxygen together from the periodic table, is 79.545. And this gives us a rough number of 3.3608 grams. Okay, so what are we going to say about this number? We are going to say that this number here is the theoretical yield of copper oxide. Alright, so where are we at? We can now put all of our numbers together, our actual and our theoretical. Remember our actual from earlier was 2.40, we said. We assumed that was the actual, and then we just worked out that our theoretical was 3.3608 roughly, then times by 100. And this gives us roughly 71.4%. Notice 3 significant figures because our recorded value were in 3 significant figures. Now, very important to note here, we made a lot of assumptions to calculate this value. We assumed that all of the copper carbonate has reacted, so that the mass at the end that we weighed is only copper oxide. We also assumed that none of the copper carbonate escaped, and so we made a few assumptions to get to this value. But that is one of the things you have to do when you're calculating percentage yield. You can critique those assumptions based on the experiment itself and work out whether they were legitimate or not, but just to get into the question and actually do some calculations, that's what we did. And so our number gets us to 71.4. It's also important to note that if you get a yield that's above 100, that doesn't necessarily mean it's a good thing. There could be inaccuracies in the design of the experiment that might lead to that. But the idea here is to calculate a value that gives you a rough estimate of how much of the reaction has gone to completion.